Great. Who's already here? Who's Naixin Zhao? Qian, sorry. Talking about simulated Raman scattering microscopy.
Right.
And so what do you need? So let's get rid of this guy. Oh, sorry. There we go. So you want to start your talk?
Thank you. Yes. Yeah, I can use this one.
Okay.
Thank you.
All right. I'll take my coffee away from you.
Thanks.
Take it away.
Let me this point. So good afternoon, everyone. I feel very fortunate to come to this workshop today. I really learned a lot from all the fantastic speakers. But unfortunately, for Dr. Wei Ming, he was really looking forward to this workshop, and he had all the slides prepared, but he couldn't come due to the family emergencies. So I'm Naixin Qian. I'm a senior PhD student from his lab. I will be presenting on behalf of him. So I'll be introducing stimulated Raman scattering microscopy, which can be viewed in some way as a quantum amplified imaging of chemical bonds. Over the next 30 minutes, I will explain what I mean by sharing the recent advancement by Dr. Wei Ming on the new theoretical framework to understand SRS microscopy from a quantum perspective. And with some application, I hope to convince you how this quantum application has really enabled wide range of applications, such as I'll highlight the super resolution vibrational imaging for biological systems, and particularly another one on nanoplastic detections with environmental implications. So I think a lot of people have talked about Raman in this seminar, and same comments. So this technique developed by Dr. C.V. Raman and won the Nobel Prize really include a lot of rich chemical information in the spectroscopy, and presumably all those like rich chemical information you can see here. I'm not sure if it's working. Oh yeah. With all of those you can see here, the rich chemical information. The only thing that's kind of limited is biological application has always been the sensitivity. People have always believed it's quite a weak process that's hindering its application in the biological systems. Stimulated Raman scattering was developed in 1962, demonstrated on bulk organic liquids as a nonlinear version of Raman spectroscopy. So unlike the spontaneous Raman spectroscopy that we're quite familiar, where the photons are scattered randomly, SRS use with another laser beam to drive the Raman transition in a coherent way, so that you can drastically accelerate this Raman transition. However, this spectroscopy was only found to be quite useful in about medical applications, starting with the development of stimulated Raman microscopy. It is Dr. Wei Ming, who was at that time a postdoc at Dr. Sunny She's lab at Harvard University, together with his colleagues, Dr. Chris Frodinger. They together developed the stimulated Raman scattering microscopy, which kind of opens up this SRS microscopy being a really powerful tool for label-free imaging of the biological systems. So this slide kind of shows a typical how SRS microscopy work. We usually have like two synchronized here. So we usually have like two synchronized, spatially temporally overlapped laser beams. One's pump and one Stokes. When the frequency difference of the two beam matches the vibrational energy of the target vibrational mode, you can have stimulated Raman scattering process to produce the signal as energy loss on the pump photons and the energy gain on the Stokes beams. And use like high frequency modulation on one beam and lock-in amplification on the other, you will be able to extract the signal and through raster scanning of the laser focus throughout the sample, you'll be able to have a fast label-free imaging with vibrational contrast. This technique is now a commercial product by Leica that you can just directly purchase from market. So Dr. Raman, together with Dr. Jixin Cheng and Dr. Yasuyuki Ozaki, recently published a review paper in Nature Photonics, really integrating the beautiful summary of what has been developed and accomplished by SRS microscopy over the years. So in this review paper, we was really excited to not only be able to talk about the technical advancement on the SRS microscopy, but also very newly constructed theoretical framework from a quantum perspective to understand it. So in this very first SRS microscopy paper, when quantifying the SRS signal, you can see here the Wei was framing the discussion from a more nonlinear spectroscopy perspective, where he would roll the signal intensity to being proportional to the molecular concentration, the Raman cross-section, and the intensity of the pump and Stokes beams. This is directly this proportionality relationship is kind of directly inherited from the traditional literatures discussing the SRS phenomenon from the nonlinear spectroscopy perspective. I guess you can just directly see here, people seldom use equal sign to actually understand the signal. For the simplest reason, you can understand that it's just if you look at the two sides of the equation, the physical units just does not match. So there's no point for drawing an equal sign here. And moreover, like people always use this kind of like numerical value of like the imaginary chi3 to describe the response. But this imaginary chi3 is kind of really reported on a molecular system because it's kind of more of a bulk materialized thing. And what people do in the field is that we would use the theoretical linear relationship between the chi3 and the Raman cross-section, which is much more well documented for different molecular systems to have an understanding of what to expect for our SRS signal. So in that way, was after his theoretical framework was developed, he kind of complained to us that how come for all these years that he just never felt unsatisfied and weird that we've been using a proportionality relationship to understand the SRS signal. So starting from 2023, so we had this inspiration to come up with a new theoretical framework to essentially draw an equal sign here, and maybe to calculate the absolute signal for SRS microscopy. So the inspiration comes from this relationship between Einstein's AB coefficient, which essentially draws a beautiful connection between the spontaneous emission and the stimulated emission process. So we was very much intrigued by the possible symmetry here. If you look at the equation, that maybe by any chance we can also define a cross-section for SRS microscopy that can be somewhat connected with the cross-section of spontaneous Raman scattering, kind of in a similar way as this relationship connecting Einstein's AB coefficient. So it turns out that it's actually quite absolutely reasonable to do so, because a similar cross-section coefficient has already been defined for a nonlinear optical process, in particularly the two-photon absorption here by Dr. Maria Govemeyer. Her name, Govemeyer, will later becomes this unit for this coefficient, which essentially defines in a way by describing the rate of the two-photon absorption equals to the number of molecules times their cross-section for the molecular absorption and the square of the photon flux. So similarly, we can also introduce a stimulated Raman scattering cross-section to characterize this intrinsic molecular response during SRS transition. In that way, we will have the rate of the SRS transition being equal to the number of chemical bonds inside the target vibrational transition inside the focal volume times this SRS cross-section coefficient and the photon flux from both the pump and the Stokes beams. Oh, here. So once we have this stimulated Raman cross-section defined, which is also in the units of Govemeyer, we can now have an intrinsic parameter from a molecular level rather than a bulk material to describe the SRS response. So my colleague, Dr. Xingao, calculate this value for different vibrational modes in common small molecules and vibrational probes. As you can see here, the numerical value of this SRS coefficient spans orders of magnitude based on previous reports, depending on different molecular systems. With the large one, with the large one here, in often cases corresponding to the situation where the molecules is having some enhancement from the electronic resonance condition. And in some of those cases, if you would notice by comparing with the two-photon absorption cross-section, they can be comparable, even higher than that of the two-photon absorption. So this actually is kind of challenging the conventional intuition that Raman transitions kind of always a weak process compared to its electronic compartments. So Wei and Xin went on to harness this approach along the quantum electrodynamics to explore the theoretical connection between spontaneous Raman cross-section and stimulated Raman cross-section. So what they found is that, again, very much inspired by this Einstein's AB coefficient, is that you can see quite analogous equations that connects the spontaneous Raman cross-section with the stimulated Raman cross-section coefficient. You can understand it in a way that the spontaneous Raman cross-section can be decomposed into two major contributions. And one contribution from the intrinsic molecular response described by the stimulated Raman scattering coefficient, cross-section coefficient, and another factor of the contribution from the vacuum electromagnetic field. So from here, by further comparing with the Fachbauer-Ladenburg equations with some certain approximations, we can also build a relationship between the spontaneous Raman cross-section and the stimulated Raman cross-section as generalization of Einstein's original equation between the AB coefficient. This equation that might call it arise provides a beautiful unification between the four fundamental molecular spectroscopy process kind of in one single equations. So this theoretical development further inspired a way to propose this concept of Raman duality. Basically, it is you can understand that it is actually the weak vacuum field from the Stokes that is intrinsic to the spontaneous Raman transition process that actually makes the traditional Raman spectroscopy cross-section appears numerically small. If we look at the stimulated Raman cross-section, which is a vacuum decoupled parameter accounted by solely the intrinsic molecular properties, then it actually can be comparable or even exceed its electronic compartments, and in the case of comparing with two-photon absorption. So under this newly developed theoretical framework from quantum electrodynamic treatment, we can also calculate the absolute signal for SRS microscopy. So if we convert everything from photon flux into commonly used energy flux, and then we can rewrite the SRS signal, for example, stimulated Raman gain to be a product of the number of the molecules inside the photo volume and the incident intensity of the palm beam and Stokes beams, and the commonly used the Raman cross-section that people have been documented in all those literatures, divided by this I vacuum. Oh, where's my laser pointer here? And I vacuum is basically the previous vacuum photon flux multiplied by the energy of the photons. So once we have that derived, we can then use it to compare how much the SRS has actually enhanced the Raman transition compared to the conventional spontaneous Raman scattering. So what we can do is that we can compare the energy of the newly generated Stokes photons between the two, and in the same given time periods, excitation pump energy and everything. And then we can theoretically calculate the enhancement factor to be around 2 times 10 to the order of 8. Here. And that enhancement factor is actually in quite good agreement with our earlier experimental estimation to be 3 times 10 to the orders of 8, if you consider the other possible experimental errors and everything. So finally, this theory also provides a new framework for us to compare the detection sensitivity between spontaneous Raman scattering and stimulated Raman scattering. It is actually not a weird question to ask. It's actually a pretty difficult question to answer in the field throughout the time, because even though SRS has been developed for a long time, people have always credited to be faster imaging methods compared to the spontaneous Raman, but not really the more sensitive one. The reason is that even though SRS provides this 8 orders of magnitude amplification on the vibrational transition, the detection methods is essentially short noise limited. On the other hand, if you consider the spontaneous Raman scattering spectroscopy, in the most ideal cases, it's essentially a background-free detection, which means in the ideal case, if you have no noise, no backgrounds, nothing, you can have infinite signal-to-noise ratio as long as you capture the newly generated Stokes photon. So such fundamental differences actually makes the two techniques with different detection regimes extremely challenging to compare in terms of the sensitivity. So Wei and Xin figure out the solution. For SRS, defining the detection sensitivity is simple. That's when you reach the short noise limited. You can, let's say we work with like signal to noise ratio 1 to 1. And for spontaneous Raman, the rationale is like this. So even if you have like a background-free detection methods, for any successful detection to make a call, you will actually need at least 1 photon to actually reach your detector. Based on the two rationale, if we plot how much pump photons were sent in the focal volume against how well the local substance response in the Raman, we can see the two lines here. With the blue one essentially corresponding to the spontaneous Raman, spectroscopy, and the orange one corresponding to SRS. You can see here the two lines cross with each other, meaning it's actually the sensitivity comparison is actually a case-by-case scenario. Here I want to highlight the area here that is above the orange line and below the blue line. That's essentially the case when you will have SRS microscopy more sensitive than spontaneous Raman spectroscopy. From a practical imaging and experimental perspective, this area effectively means you're working with fast scanning with low pixel dwell time in the case of like imaging, and the sample with high local Raman response that could come from like high local concentrations or Raman probes with large cross sections. The sensitivity comparison fundamentally explains why SRS is clearly more superior over spontaneous Raman, particularly in the application of imaging and microscopy. Alongside with the innovation from all other perspectives, such as like instrumentations, chemistry, and data science, SRS microscopy has opened up a wide range of applications in many different areas, such as in biology and environmental science. This review really presents a good summary of the topic. Here, I'll just highlight a few. So one of the most transformative development in the field of SRS imaging is probably the introduction of vibrational probe, which kind of completely expanded and revolutionized the functionality beyond the conventional label-free chemical imaging, which was at the initial development of SRS microscopy thought to be the key advantages over conventional fluorescence spectroscopy and microscopy. So by introducing Raman tests, you can do a tag as small as like isotopic atoms. That way, you can introduce this test into small molecules without perturbing their biological functions too much, with minimal perturbations. And then you can have their vibrational resonance shifted in the cell-cellular region for a more specific imaging and better sensitivity. You can also couple the vibrational test with other sensing modalities or structure targeting motifs to enable functional imaging of like cellular activities or like specific cellular structures. Moreover, you can harness the especially sharp Raman resonance to enable applications such as multiplexing. So from a systematic engineering of the mode frequency, as well as the proper engineering on the sensitivity enhancement mechanisms, such as electronic pre-resonance conditions. So this concept of super multiplex vibrational imaging was demonstrated. This is kind of pioneered by our group's alumni, Dr. Lu Wei, who is right now a professor at Caltech University. That effectively what we achieve is breaking with a sharp resonance and a lot of vibrational colors, we can effectively break the color barrier that's limited by the traditional broadband fluorescent microscopy from simultaneously 3 to 5 colors to more than 20 colors imaging. So the development of electronic pre-resonance enhanced probes also for SRS actually also nourished the development of Raman encoded fluorescence spectroscopy. This is actually a concept proposed quite long ago by Dr. John Rice, but was only successfully achieved and demonstrated in 2019 because of this drastically enhanced Raman cross-section with probes under the proper electronic pre-resonance condition. Harnessing this sensitivity from this, harnessing the sensitive like background-free detection from working with fluorescence detection, our group's alumni Dr. Han Qinxiong and Dr. Li Xueshi successfully demonstrated stimulated Raman excited fluorescence using the electronic pre-resonance probe Roman 800 at a single molecular level. So this is a, where's my laser? Yeah, this is a single molecular spectrum, a vibrational spectrum that they get from a single Roman 800 dye. And this single molecular sensitivity actually kind of also showcased under a proper electronic resonance condition, SRS transition can actually be quite pronounced to give you such high alternate sensitivity. The introduction of fluorescence detection in Raman imaging also opens up a new avenue to adopt the methods established in super resolution imaging based on fluorescence for super resolution vibrational imaging. For example, in this work, Dr. Han Qinxiong and I collaborate to implement this Nobel Prize winning technique by Professor Stephen Hell on the stimulated excitation depletion techniques. So in his methods, you have a donut beam with a high power to deplete the excited molecules surrounding the focus in the excited states. And what we do is that in that way, you can reshape the point spread function to beyond the diffraction limit. Because we're working with fluorescence here, detection here, we can also implement this strategy by adding a donut beam to achieve super resolution of vibrational imaging in together with the frequency modulation functionality we introduced on the Stokes beam. With this, we successfully demonstrated the super resolution beyond the diffraction limit with 2 folds of resolution enhancement. Compared to other super resolution attempts in the working with Raman imaging and vibrational imaging, the benefits of our technique is the capability of using relatively low power, so that is particularly compatible with imaging the biological systems. And here we demonstrated together with the development of stimulated Raman enhanced fluorescence dye, we demonstrated specific structure labeling and super resolution imaging of the membrane structures and the newly synthesized DNA in cells. Finally, in addition to bioimaging, I want to talk about the application in environmental science, which is our group's kind of like the focus in recent years on the detection of micro nanoplastics. So the global plastic pollution has been a real crisis. I think probably everybody's seen this in the news. In particularly for the topic of microplastics, which is defined by the plastic particles with size smaller than 5 millimeter and above 1 micron. Many people throughout the years since the first discovery of microplastics, even though the plastic is considered non-degradable, they apparently do fragment into small particles. Ever since the first discovery, there are like growing attentions from not only the academic wise, but also from the general public on the possible consequences and how bad the situation is on the microplastic detection. So moreover, one general belief is that for those plastic particles, as they get smaller, you generally expect more of them, because if you have one microparticles fragmenting into nanoparticles, say 1 micron into 100 nanometer, you are effectively having thousands of them because of the same mass. However, analyzing nanoplastic has been a real challenge because of the Oh, is it time?
You've got 2 minutes, including all your questions.
Okay, so I'll do very quick. So analyzing the nanoplastic has been real challenges because what people have been using as a gold standard methods for microplastic detection is usually the imaging-based vibrational microscopy, such as spontaneous Raman and FTIR. But they usually don't have the sensitivity and resolution to go down the nanoplastic regime, even though people believe there are more of them, and people believe that they have higher tendency to cross the biological barrier and cause damage to biological systems. So in this work from our group, we developed a nanoplastic detection platform based on SRS microscopy. As I'll just highlight the sensitivity-wise, I guess I probably already convinced everybody. I'll just highlight the social impact here. This detection from the bottled water has been covered by 700 media worldwide. People are really shocked about how many plastic particles we found in bottled water, which is about 250,000 per liter, and really shocked about the heterogeneity inside those samples. That is not just the plastic packaging that's releasing the particles. We're detecting plastic particle types way beyond the pure packaging material. And it's even brought by the congressional hearing as a potentially useful technique to help people evaluate what's the prevalence and the consequences of the nanoplastic contamination. To close, I hope to convince that SRS microscopy, which can be viewed fundamentally as a quantum amplified microscopy for chemical imaging, has really profound utilities in addressing many real-life challenges with biological and environmental implications. Finally, we would like to acknowledge our current group member, Dr. Singao, and on the theoretical development part, and me on the development of super resolution and the nanoplastic detection part. We are deeply grateful for our fantastic collaborators and the funding sources that have been supporting our works. And thank you so much for your attention. Happy to take any questions.
We have the coffee break now, and it's only 15 minutes. We're 2 minutes into it, so we've got 13 left. I think we'll take one question just so we don't eat into the coffee break too much more.
Yeah, I'll be around. So
Very insightful theory, Naixin. Right now, your theory predicts your efficiency would just go up linearly with eye pump. But at some point, you will start to see saturation, I believe,
yes,
right? Because
yes.
you're going to compete with the Rayleigh channel. Is there any way to factor that in as the denominator?
So I didn't put it in. Oh, well, it's way slides, but yeah, we discussed about it in our theoretical papers. If you're interested, I can definitely share that paper to you. You can build a model to consider that. Actually, it's actually quite interesting to study what is the energy you can input to a point that you are basically saturating, and what's the best condition for the imaging. We have a thorough discussion session in the paper on that based on the rate. When we consider the SRS transition rate, is pretty convenient for us to actually look into this in the model. Yeah.
I'll read it. In fact, Wei has emailed to me, but haven't had a chance yet.
Yeah.
I think just in the interest of time, we will end this part of the session now, and I guess you'll have an opportunity to talk to the speaker in the coffee break, if that's okay. So thanks, everyone.